My title is very ambitiously 500 Years of Mathematics. Why have I chosen this title? We celebrate this year the birth of Thomas Gresham in 1519. And so I gave myself the task to think what has happened mathematically since Thomas Gresham was born and what will happen in the next 500 years. So no small task. Okay. So when I started to think about this, I realized that Thomas Gresham couldn't have been born at a more interesting time mathematically, because his birth, or 1519, in very many respects marks the division between what I would call ancient or classical mathematics, the mathematics of the Greeks and then the Arabs, and modern mathematics, the mathematics that we celebrate today. And I illustrate this on the left with a proof of Pythagoras' theorem using geometry, which is how Euclid did it. And on the right, we have calculus and a bit of statistics there as well, if you spot it, showing the mathematics that has happened since. So what I want to do is take you through 500 years of maths. Now, it is impossible to do justice to 500 years of maths in 1 hour, or indeed 100 hours. So what I've decided to do is to look at a few things which happened at around about the time of Thomas Gresham and show you how they have gone on to dominate modern mathematical thinking. And I apologize for all the bits of maths that I've left out in the process. I've put a few more in my transcript, but as I said, I've only got 1 hour to do an awful lot. So 1519 really does mark the division between classical and modern maths. It's where mathematicians got confidence that they could do something which the Greeks could not do. And that forms the start of my talk and will be a theme which goes through all the rest of the talk. So what is this great thing? What is this great thing? Well, it's the solution of the cubic equation. So let me tell you a bit about this. So here we have the quadratic equation. Ax squared plus bx plus c. I should have put equals 0. Apologies for that. And that equation has been around since the time of the Babylonians. And the reason it was of interest to the Babylonians is that it's an equation to do with area, and the Babylonians needed to calculate areas in order to work out how much tax to pay. Okay. So that equation, the quadratic equation, has been around for a very, very long time, and it was found that you could solve it. And here is the solution to the quadratic equation. I imagine many of you are familiar with this. And that solution was sort of known to the Babylonians, sort of known to the Greeks, and in its modern form was derived, we think, in India. So that is the solution to the quadratic equation. But underneath it, we have the cubic equation. Now, the Babylonians knew about the cubic equation because it relates to volumes. And they actually had tables of solutions, which they calculated approximately, to this equation. But nobody knew how to solve it exactly. And this question was open up to the birth of Thomas Gresham. So what happened next? Well, what happened was in the 1520s, so the decade just after Gresham was born, a guy called Scipione del Ferro solved the cubic equation. And as I said, this was the first thing that had been done, which was new since the Greeks. Well, stuff had been done by the Arabs as well, but they weren't actually that familiar with it. As far as they were concerned, this was new. So Scipione looked not at the general cubic, but at this particular example, ax cubed plus cx equals d, which, as I say, is an equation in volumes. And any cubic equation can, by a relatively simple transformation, be put into this form. And I thought, well, this is my last lecture of the series. Let's do some real mathematics. Yes, good. So let's see how Scipione solved it. So Scipione said, look, let's think of there being two other numbers, u and v. So the difference is d, and the product is c cubed over 3. Now, it's possible, if you take v, then that's this divided by u, you bring that over there, and you find that u satisfies a quadratic equation. And once you've found u, you can find v. So these two numbers can be found by solving a quadratic equation, and we know how to do this. So I don't know how Scipione thought about this, but there we are. There, you come up with those two numbers. And then what you do is you say, well, let x be the difference between the cube roots of those two numbers. And then if you cube it, and they knew the formula for how to cube, so you cube this expression. If you cube u to the third, you get u. If you cube minus v to the third, you get minus v, and you get this stuff in the middle. U minus v, we've already said is d, and you can pull out a factor, 3uv to the third, and that is x from up there. That is c, so you get x cubed equals d minus cx. Ta-da! You have solved the cubic. So providing you can find cube roots, and that's kind of expected, you can solve the cubic, and there we are. So that was a major achievement. And like all major achievements, even in mathematics, it led to a punch-up. Okay. So let's have a look at the punch-up. So this guy here called Tartaglia, also known as the stammerer, came up independently with a solution to the cubic, and in fact, a more general case of the cubic. But he was very suspicious that someone else would steal his ideas, so he expressed his solution in the form of sort of an anagram and a poem, as things were done in those days. And he told this guy Cardano, who was one of the other mathematicians at the time, but he swore Cardano to absolute secrecy. But then Cardano became familiar with the other solution by Del Ferro, and he thought, well, he should give Tartaglia credit, so he wrote a book in which he explained Tartaglia's solution, and Tartaglia was not pleased about this, and there was a big punch-up as a result. But the bottom line is that the cubic had been solved, and it had been solved in the time of Gresham, and that was the first thing that had been done, which was new since the time of the Greeks. And that gave everybody a lot of confidence that they could do new stuff. So what I want to do now is tell you what the solution of the cubic led to, just that thing on its own. And it led to an enormous amount of mathematics just on its own right. So you solved the cubic equation. What's next? Well, obviously, the next type of equation you might want to solve is one, instead of a cube there, with a fourth power, the quartic equation, and fairly quickly it was found that you could solve the quartic. I won't put up the solution, it's a bit technical, but it can be done. So the next question was, well, can we solve the quintic equation? There it is. So this equation doesn't have a direct link to volumes like the cubic, it's more of a kind of thing of mathematical interest, although equations like this are now used all the time in computer graphics to represent surfaces. So if you see something like an animated movie, the chances are the shapes in that will be satisfying an equation something like this. And people tried very, very hard to solve this equation, using the same sort of tricks and ideas that had been used to solve the cubic and the quadratic and the quartic. And no one could solve it. And after a while, people began to think, well, maybe there isn't a way of doing it. And Abel, who was a Norwegian mathematician, who, as you can see, was extremely young, at the time, was the first person to show rigorously that the quintic equation could not be solved by extracting cube roots, fourth roots, and fifth roots. It was an incredibly major piece of work. Abel did lots of other stuff, and he would have done much more stuff had he not died young, but now one of the main prizes for mathematics is named after him, the Abel Prize. Following closely on to Abel was Galois, here we are, who also died extremely young. Abel died, I think he died of blood poisoning. Galois was shot in a duel. And at the age of 19, Galois also managed to show that the quintic equation did not have a solution. And whilst Abel's proof, though correct, was very technical and rather specialized, Galois developed a branch of mathematics now called Galois theory after him, for which the solution of the cubic was just one of the consequences. It had many, many other consequences. Galois is generally regarded as one of the all-time great geniuses of mathematics. Unfortunately, he was also revolutionary and came to a very sticky end, as I have pointed out. What else did Galois manage to show as a result of generating Galois theory? Well, he resolved two problems which have been around since the time of the Greeks. One of which was, could you trisect the angle using ruler and compasses? And he showed that that was not possible. Also, another one from the Greeks was, could you construct a cube which has volume twice the original, which is equivalent to solving the cubic equation, x cubed equals 2. So that's another link in with the cubic. And Galois was able to show that that could not be done with ruler and compass. And that was all done using his theory, which he developed at the age of 19. No pressure. Okay. What else came out of Galois' theory? Well, I'd say Galois developed this theory to solve the quintic equation, solve those two problems at the same time. And Galois' theory, or part of it, the theory of modular forms, is now used all the time in such devices as mobile phones and CD players to encode information onto these devices in such a way that it is error-free. And all of that follows from his theory, and none of that would have been really thought of if he hadn't tried to solve the quintic equation. So we see how this kind of theme ripples down the ages. Galois, as well as developing Galois theory, formulated a lot of the mathematics of symmetry. He was able to show that the quintic equation didn't have a solution by showing that if it did, there would be certain symmetries between the roots, and those symmetries were just not present in certain equations. And to study the symmetry of these equations, he developed that branch of mathematics we now call group theory. So group theory is the theory behind symmetry. It's the theory behind how things combine together to produce other things and the sort of structures that you get. Again, developed to help solve the quintic. Group theory is incredibly relevant to studying symmetry in objects like octahedra, icosahedra, and so on and so on. And that's very, very relevant to modern chemistry. So group theory is important in studying crystal structures. Group theory has everything to do with how objects are rearranged when you transform them. And when I went to Cambridge back in 1979 as an undergraduate, Rubik's Cube had just come out, and we found, as mathematicians, we became extremely exciting people because we could use group theory to solve Rubik's Cubes, and that made us kind of cool for a while. So there we are. And unfortunately, group theory, well, not unfortunately, I have to confess, guys, I'm a Morris dancer, and you can use group theory to help design Morris dances. Okay, so I'm in there somewhere. And it has many, many applications. And as I say, this is 500 years of mathematics. I want to celebrate all the great achievements in the last 500 years. And whilst I was at Cambridge in 1982, amazing theorem was proved by John Conway and various others, which managed to classify every single group that you could have, or in particular the finite simple groups, and that sort of tied up the entire subject of group theory, or finished the basic classification of them, and that theory is regarded as one of the big achievements of the last 500 years of mathematics. And boy, did we have a party in 1982. I was nothing to do with the theory, but the alcohol was widely spread around on that day. So that's one sort of thing that solving the cubic led to. It led to solving the quintic, led to group theory, which led to many, many other things. But it led to something I think of as even more important, and that's the understanding of the importance of complex numbers. So going back to the quadratic equation, here we have it. There's the quadratic equation. And anyone that's ever tried to solve the quadratic equation, and I imagine many of you have at some point in your life had to solve the quadratic equation, will have noticed that you have this square root term here, which has b squared minus 4ac. And if 4ac is bigger than b squared, you have a minus term in here, and as we all know, you can't take the square root of a negative number. Well, at least you can't take the square root and end up with another real number. So the Babylonians knew about this, the Greeks knew about this, and all they basically said was, well, if this is negative, it doesn't have a solution, so we won't worry. Okay. You can solve it, but you have to do something which mathematicians love doing, which is if you can't solve something, you invent something else, which is the solution, and then you solved it. Okay, which isn't quite as stupid as it sounds, but mathematicians resolve this by saying, let there be a new number I, which has the property that when it's squared gives -1, and we can call that the imaginary number, and then we can go and look at what properties that has, even if it doesn't really exist. And lots of maths is like that. And suddenly you find it's all very useful. So this was developed really so you could solve things like this. So give an example. If you take the quadratic equation x squared plus 4x plus 5, which we're going to meet again later in the talk, so remember it, guys. This has solution x is -2 plus I and -2 minus I. Okay. So what? Well, as I say, the attitude of the Greeks and the earlier mathematicians was that if the quadratic equation had a negative sign onto the square root, then it doesn't have a solution. And there's one branch of understanding which says if something can't be solved and doesn't have a solution, it's not worth solving. But then the people that were interested in the cubic, so Cardano again and another mathematician called Combelli, noticed that if you wanted to solve the cubic and you use this strategy, which I explained earlier, where you look at these two numbers u and v, which satisfy a quadratic equation, then sometimes there are examples of cubic equations for which the two numbers u and v satisfied a quadratic equation which could not be solved. However, if you solved it in terms of these funny complex numbers and then looked for the solution x of the cubic in terms of them, the number you got actually was a real number. In other words, by going through the complex realm of solving an equation in complex numbers, you could actually find a real answer to a real problem. And that kind of made complex numbers respectable. So even though they couldn't actually make any sense of what the number I meant, it turned out to be very, very handy in computations. And that made them respectable, and people started studying them very seriously. And without complex numbers, much of modern mathematics, science, and engineering would not be possible. So here we are, another major part of mathematics which came out of solving that problem which arose at the time of Thomas Gresham. Okay, so those are complex numbers. So just to kind of finish polynomial equations off, here is the great Gauss, Carl Friedrich Gauss, who in many people's opinion was the finest mathematician of all time. And he proved a result called the fundamental theorem of algebra. And the fundamental theorem of algebra said that any polynomial equation that you can write down can always be solved in terms of complex numbers. In other words, once you've got the complex numbers, you can solve all polynomial equations. And that was a very, very important result. Again, one of the other big theorems in mathematics. He didn't show you how you could solve it, but he did show that he had a solution. So that's a start. Okay. Later on, we're going to come across an equation where we don't actually know whether it has a solution or not, which is a bit more worrying. So there's old Gauss, one of the greatest mathematicians of all time. Here is another one of the greatest mathematicians of all time. This is Euler, who sort of came before Gauss and after Newton. One of my favourite mathematicians. He had a great sense of humour and was still publishing vast amounts of mathematics 50 years after he died. He had so many notebooks and he lived to such a long age that people were still writing up his stuff long after he died. And Euler's had a huge number of results. I think they had some poll recently for the 5 best formulas of mathematics, and 3 of them were due to him. Okay, quite incredible. I'll come back to this at the end of my series next year. But possibly his most important achievement was that he found a link between these complex numbers that we're looking at to solve polynomial equations and trigonometric functions. Now, I want to kind of dwell on this for a minute. The Greeks knew all about trig. Trig is triangles, its properties of triangles. They knew about the functions sine and cosine, which are the opposite and adjacent sides of a right-angled triangle. Okay, so these are functions which have been known about and studied in the context of geometry. Polynomial equations were quite different. They were the realm of algebra. They were how numbers combine with each other. And what Euler found was a link between geometry, professor of geometry, and algebra. We don't have a professor of algebra, but we don't need one because they are the same subject, and Euler found out why. Okay, so he found this link. Okay, so the next slide's a little bit technical, but we need to get through it. Euler came up with this number. Now we know it as Euler's number, or E, which is this limit. It's 1 plus 1 over n to the n. And this number comes up very naturally in the study of growth and in particular of compound interest, which is how he was thinking about it. And it has a value. It's 2.718281828, or it's 1 plus 1 over 1 factorial, 1 over 2 factorial, and so on. So this is Euler's number. It's one of the great numbers of mathematics. It's up there with pi as one of the great numbers. And that is a graph of e to the x as a function of x. So Euler studied this number in the context of how things grow and compound interest. And then he thought, hell, what happens if you let x in the formula e to the x be a complex number? Okay? We've got these things which are crazy already. Let's do something even crazier. And this is what he found. He found that if theta was a normal number, real number, and I is the square root of minus 1, that e to the I theta is cos theta plus I sine theta. An incredibly important formula, one of the most important formulas both in the theoretical nature of mathematics and also the practical applications of maths. And there we have a link between I, which comes out of polynomial equations, E, which is this function to do with growth, and there the trigonometric functions sitting there looking at us. And you can, from this, find that cos theta is e to the I theta plus e to the minus I theta over 2. Sine theta is the difference divided by 2i. And if you put theta is pi into this expression, you get e to the I pi equals minus 1, or if you prefer, e to the I pi plus 1 equals 0. And that formula wins hands down as the best formula in mathematics ever produced. Okay, every poll puts this top. I do a poll my students each year, and I have to deliberately exclude this formula because otherwise they all come up with it. Okay, so that's Euler's identity, which he proved in the 1700s, so the 18th century, linking polynomial equations, trigonometric functions, and this number e. And we'll come back to this in a minute as well. But I just want to sort of finish this sort of first section of the talk, which is largely about algebra and polynomials, with just the kind of big problem in algebra, which was only solved very recently, which is Fermat's last theorem. So I think many of you may have heard of this. Here we have Fermat, and in 1637, which isn't very much long after Gresham College itself was founded, so Gresham College was in the end of the 16th century, Fermat, in the margin of a book, wrote, here's the equation a to the n plus b to the n equals c to the n. I have found a truly marvellous proof that this can never be solved if n is greater than 2 and a, b, and c are integers. Now, to give Fermat credit, the case of n equals 4 was proved by him, and we know that, and there's lots of evidence for this. The cubic case, going back to the cubic equation, keep the theme going, was done by our friend Euler. Okay, it's significantly harder. Fermat did the case n equals 4 by factorising. You couldn't factorise the case n equals 3, but Euler managed to find a way around that. But no one managed to find a general proof during the time of Euler, and certainly not one which would fit into the margin or anything close to the margin. And 450 years later, it's not quite 500, but not far off, this was at last solved, and the efforts to prove it led to lots of new mathematics, so algebraic number theory, modularity theory, lots of notoriety. There was a prize for it, which lots of people tried to win and didn't. And there's an entire Star Trek episode based around Fermat's last theorem, should you wish to watch it. And it was finally proved in 1995 on the left by Andrew Wiles, who was working in Princeton at the time. And everyone has heard of Andrew, but we mustn't also forget that it was a collaboration with this guy, Richard Taylor. And they worked together to finally prove Fermat's last theorem. And that's 1995, so 450 odd years after Gresham, and that again is one of the big achievements in the last 500 years. I'd just like to say, basking in reflected glory, that when I was at Cambridge, I was vice president of the Cambridge Math Society, otherwise known as the Archimedeans, and the president was Richard Taylor. Okay, so I have to put him in there. Okay, so that's algebra, and that came out of the cubic equation, which was thought of just after Gresham was born. But something else happened just after Gresham was born, and that led to another branch of mathematics and another area of understanding, and that was the publication by Copernicus of the heliocentric theory of the planets. So up until the time of Thomas Gresham, the basic theory about the planets was that they all went around the Earth, and the Earth was stationary, and the Sun went around the Earth as well, the Ptolemaic theory. And it was only just after Gresham was born that Copernicus turned all this round and published his theory, which was that the Earth went round the Sun and the planets went round the Sun on circles. Interesting fact, in 1519, Copernicus formulated a theorem in economics, which has since then become Gresham's law. And it is the same Gresham, I checked. So Thomas Gresham produced this law in economics, which I think is something like bad money drives out good, or something along those lines. I'm not an economist. It's sometimes called the Gresham-Copernicus law, and Copernicus got it in 1519. And even though Thomas Gresham was incredibly gifted, I don't think he did it in 1519 himself. Okay. So hard on the heels of Copernicus, Kepler in 1610, using a lot of data produced by Tycho Brahe, who Kepler was Brahe's student, took those data, combined it with Copernicus's way of thinking about the planets, and came up with Kepler's 3 laws of kinematics. The first, that the planets went round the sun in an ellipse. The second, that planets swept out equal areas in equal time. That's called the conservation of angular momentum now. And the third was that the square of the period of motion was the cube, proportional to the cube of the size of the ellipse. These are extremely important laws, I say again, just after Gresham was founded. Why are they important? Because they perfectly described planetary motion really very accurately. And from that description, you could predict forward very, very accurately, and it made everyone realize that the Copernican view of the world was the correct view of the world. Okay. So these were laws of kinematics, again, just after the time of Thomas Gresham. So these are laws of kinematics, which are descriptions of how planets move. And shortly after that, we get the laws of dynamics, which are the explanation of why they move in that way. So the 2 big heroes of this for me are Galileo, who was born in 1564. So again, not long after Gresham was born. He was born on the 15th of February, which is my birthday. I'm slightly younger than him. And he died in 1642. And just to keep the theme going, Newton was then born in 1643 and lived through to 1727. And between the 2 of them, they formulated the basic laws of mechanics, which have acted as the bedrock for much of physics ever since. One of the laws that Newton, the Principia, by the way, was published in 1692. And one of the laws that Newton published in the Principia was the law of universal gravitation, which is that if you have 2 bodies, x and y, at positions x and y, then the force between them was proportional to the mass, product of the masses of those 2 bodies, divided by the distance between the 2 bodies squared. So that's Newton's law of gravitation. And what Newton did was he took that law of gravitation and he used that to deduce Kepler's 3 laws of motion. Again, an incredible achievement. So these laws that Kepler had formulated by observation, Newton was able to show mathematically had to be true, provided that you had this law acting. Okay. So it's really interesting the way that Newton published this. Newton published his results in the Principia in Latin. And as I said, Gresham's birth marks the division between modern and classical mathematics. And Newton decided to formulate his explanation in classical terms. So not only did he publish in Latin, but he put all of his results in the language of geometry. Okay. But Newton didn't derive them using geometry. What Newton did was he derived them using his own method of calculus. So he got them with calculus, and that's how we do them with students nowadays, but he expressed them in the language of geometry. So, calculus. I'm now going to say something really, really arrogant or bold or whatever. So this is my opinion. In my opinion, the invention of calculus is the singular most important bit of mathematics which has been done in the last 500 years. I'm not saying there's been a ton of other stuff which is important, but in my opinion, that's the big one. And here's even more awkward. I think it as the single most important creation of the human mind. I'm happy to argue that with you later, I don't think many people totally disagree with the first one. I mean, and whatever your thoughts, the invention of calculus is a decisive moment in the kind of development of mankind. Okay, so what is calculus? Well, calculus is basically the study of how things change. That's all it is. And the two concepts which Newton introduced were one which was the derivative. So if you draw a graph of a function f, then the derivative is the slope of the graph. If f is the position of an object, then the slope of the graph is the speed of the object. Okay. The other concept is the integral, which if you have a graph, it's the area under the graph. So equally, if I draw a graph of the speed of an object, then the area under the graph is the distance travelled by that object. So those are the two fundamental concepts of calculus which Newton kind of came up with. Just here's a bit of technical stuff. You can define the derivative as the limit of the difference between two things divided by, so if you take something evaluated at this number h, take off the other one and divide by h and let h tend to 0. That gives you your derivative. The inverse is the integral. And here's an example, the cubic again. There's its derivative and there's its integral. So Newton worked all this out. And then he used the calculus to, as I say, find the equations of motion of the planets from first principles. Again, this led to a punch-up. Why did this lead to a punch-up? Well, Newton kind of claimed credit for the calculus, and the British mathematicians all rallied behind him to claim credit. But arguably, this guy also deserves credit for it. This is Leibniz, who, another true genius, a true polymath, living in Hanover, came up with many of the same ideas and a far better notation than Newton. And indeed, the way we think of calculus and write it down nowadays is largely following Leibniz. However, many other ideas for calculus were floating around the time in Europe and even in India. And there's lots of evidence that the Indian mathematicians were thinking the same way. Ideas which were again bubbling up around about the same time as Thomas Gresham. Now, I've told you about Euler and his discovery of the link between complex numbers and trigonometric functions. Euler did something very important in calculus. Leibniz and Newton were both thinking in terms of functions changing in time. Euler then went on to extend it to look at the way things change in time and space and introduced the idea of what are called partial differential equations, which are descriptions of the way things change in time and space. And these rather ferocious things, which Euler derived, are the Euler equations. And if u is the velocity of the air, that's how it changes in time. This is how it changes in space. That's the pressure. And to a rough approximation, those are the equations of the weather. And that's what we solve every day when we solve the weather. I'll give you some more extended versions of these towards the end of the talk when we talk about where maths is going in the next 500 years. So here we are, partial differential equations. These are descriptions of how things change in time and space. And again, controversial opinion by me. Ordinary, that's equations which depend on time only. And partial, ones which depend on time and space, are one of the most powerful tools that we have for studying problems in physics, engineering, and biology. They are the fundamental way of describing pretty well all physical and chemical and biological processes. Newton came up with the basic idea behind them, and that was in the 1600s, and 400 years later, we still know damn all about them. Okay, this is how mathematics is sometimes. In fact, my job is to find out a bit more about them. Let me tell you what we do know about them. This equation here, which looks a little bit like a quadratic, and there's reasons for that, is called a linear second-order differential equation. And this sort of equation here arises all the time when you study vibrations in mechanical and physical systems. And Euler worked out that you could solve this by substituting in a solution x, which involves his famous number e raised to the power lambda t. If you substitute this into here and do some manipulations, you find that lambda satisfies a quadratic equation. Remember where we came in, beginning of this lecture, quadratic equations. We know how to solve these. The solution of that is this. It involves these scary numbers I. Euler didn't worry about that. He said, okay, that's what the solution looks like, but I know that these are related to sine and cosine, and if you substitute in his formula, you get that the solution is this. And here's an example of, there's an equation for vibrations. You go through all this complex number stuff, and you end up with a solution which is perfectly physical. Okay, so that's rather good. And this describes damped harmonic motion, which looks like that. And if I do this, okay, all that, the microphones wobble around for a bit, come to rest, perfectly described by that. If you have more complex differential equations, ones involving third derivatives, you get back to the solution, the cubic, again. So it comes up everywhere. If you want to do something more complex, this is the equation here for the motion of the pendulum. Those of you who went to my talk on chaos will have seen this equation. And this is one of the many equations which we cannot solve. There are two ways of solving this. One way is to say, let the solution be a function, and we'll call that function a name, and now we've solved it, which is sort of true. The alternative is to solve it on a computer, but again, in terms of kind of the evolution of mathematics, two great discoveries in the 19th and then early 20th century allow us to really make big inroads. One was Poincaré, who found that by combining differential equations with geometry, back to professorship of geometry, you may not be able to solve them exactly, but you can draw a picture to show what's going on. And then in the early 20th century, Emmy Noether, arguably the greatest female mathematician of all time, arguably one of the greatest mathematicians of all time, combined differential equations with the group theory that Galois had come up with and found fantastic links, and that's led to enormous results in physics. Okay, so that's where Thomas Gresham, Copernicus, and all that's led on to. So that's the end of my kind of second section. So I want to talk about now some of the other things that have happened since Gresham. One is the what we call linear algebra and matrices. So this is a very unglamorous. Everyone knows about Fermat's last theorem. They've made movies about this. No one's yet made a movie about matrix theory, but I think it's possibly one of the most useful bits of maths with many applications, including Google and even Brexit. I wrote an article for the Times about this. So here's a little question. Let's see if we can solve it. There's my daughter. This is her Facebook page. And I was 32 when my daughter was born. Our combined age is now 86. How old are we? Can anyone solve that? So this is a sort of puzzle, again, people were looking at the time. 7? No, I'm not 7. Sorry, what was it you said? 27. Yes, she is 27 years old. How do we do that? By the way, fantastic. So the way to do it is we do some algebra, again, a bit like the cubic. That's my age. I'll call myself X. My daughter is Y. I was 32 when she was born, which means I'm 32 years older than she is. So X minus Y is 32. Our combined age is 86, so X plus Y is 86. And the direct way of solving this is you add these two together. The Y's cancel, and you get 2X's 118. And you find out from that I am 59. Ha. And if you subtract, you find that my daughter is 27. So you're absolutely right. So that's a trick. There's lots of books on recreational maths which involve similar kind of stuff. But this doesn't generalize very well. And if you want to solve more kind of challenging problems, the maths that you use was developed in the 19th century by a guy called Cayley in Cambridge. And that he thought, well, the way to kind of solve these problems is to think about the sort of structure. And he invented a thing called the matrix. So this is a matrix here, 1 minus 1, 1, 1, and laws for how you use these things. And the law for x minus y is 32, and x plus y is 100. That should be 118, apologies. Looks like this, expressed in matrix form. Now, why is this important? Well, this sort of way of writing things down in terms of matrices is very, very useful in two dimensions or in 3 dimensions to look at geometrical transformations. And this is the basis of much geometry and now computer graphics. And if you do it in 4 dimensions, it's the basis of special and general relativity. So it's a very, very powerful concept, all coming out of the need to solve things like that. If you want to solve our equation, what you do is you construct a thing called the inverse of the matrix. So if A times xy is AB, you sort of divide by the matrix, xy is A inverse AB. For our problem, A inverse can be calculated to be that, and that leads to this solution, which is the one we got by adding them together and dividing by 2, or subtracting and dividing by 2. Well, why should we bother? Who cares how old my daughter is? Well, I care how old my daughter is, but who in general cares? Well, solving equations like this with many, many unknowns is actually rather important to modern society. Here are some of the applications. You can read them for yourself for solving many, many unknowns, but certainly my own area of weather forecasting and the general area of the internet all rely on doing that sort of matrix inversion. If we couldn't invert matrices, we couldn't basically have technology. The first algorithm to do this was come up with by Gauss in the early 19th century. We still use this, although it's a bit slow. Modern algorithms like conjugate gradient and multigrid, again, I'm afraid this is sort of my day job, are what are used all the time to solve many of our day-to-day problems. So when you book an airline ticket on an airline, that is booked by solving this sort of thing. When you look something up on Google, that's done by solving these sort of equations. So I've used the word here, algorithm, which leads me neatly into my final kind of section on what I think is important, which is algorithms. And this will bring us back to the cubic. So one of the main ways that the mathematics that I do impacts, or anyone does, impacts on your lives on a day-to-day basis is through algorithms. I've already mentioned Google, the internet itself, all the things that make your mobile phone work, Amazon, even dating websites are driven by mathematical algorithms. And the first algorithms were developed, guess what, to solve polynomial equations, the same equations that we started the talk with. The Babylonians actually came up with an algorithm for solving the quadratic equation. And there we have an example, x squared equals 2. And their kind of perspective was, well, if you want to solve this, if x is a solution, divide 2 by it, take the mean, that's probably better. And if you start out with 1 as a guess, then 2 divided by 1 is 2, 1 plus 2 is 3, 3 over 2 is 3 over 2. That's our next guess. Substitute that in, you get this, and in, and very, very quickly, you end up with a solution, an approximate but still extremely accurate solution of the quadratic equation, and that's the solution to a few more decimal places. Okay. So that was our first algorithm, developed to solve quadratic equations, and it was extended very quickly to solve the cubic equation. There's a cubic equation using a method that Newton came up with. So if you want to solve the general equation f of x equals 0, xn is a guess to the solution. You can get a better guess, xn plus 1, by saying xn minus f divided by its derivative. This is called Newton's method. That was one of the first really important algorithms, and that is used all the time in modern computers to solve problems, certainly in such subjects as weather forecasting If you take the cubic, there we are, then there's Newton's iteration for solving this. And that works very, very effectively to help you find the solutions of the cubic. So these are algorithms which were developed to solve polynomial equations. Now algorithms are everywhere. I've just listed a few. If you want to solve a differential equation, you use the Runge-Kutta method. If you want to work out a Fourier series, in other words, do anything to do with signal processing, in other words, mobile phones, you use the fast Fourier transform. If you've got lots of data coming in and you want to update your knowledge of a system, you use the Kalman filter. Again, that's used in mobile phones. And if you want to find a website, you use the Google PageRank algorithm based on linear algebra. These are just 4 algorithms of the many that are used, but I would say those are probably 4 of the most important. And these are, of course, all implemented on computers. And if it wasn't for various mathematicians, here are perhaps the 4 most important: Babbage, Lovelace, Turing, and von Neumann. We wouldn't have computers, and therefore we wouldn't have the modern world. So the invention of the computer is, again, a hugely important thing that maths has done for us in the last 500 years. When I wrote this lecture, I posed the question, given we've done all this, are we living in a mathematical golden age? And I would strongly argue that the answer to that is yes. I think we are. I find it incredibly exciting to be around as a mathematician at the moment. I have 3 reasons for believing this. My first reason is just using my eyes. So lots of long-standing mathematical problems are being solved, and that includes Fermat's last theorem, Poincare conjecture, and lots of new exciting problems are being posed. So that's one reason. Second reason is that the fusion now between mathematics and computers and all the data that we've got allows mathematicians to be really creative and deal with major problems of huge complexity that were completely out of reach of people in the past. And thirdly, the number of applications that we see for maths is just growing exponentially. There seems to be no limit to it. I'm at a workshop at the moment in Nottingham. I shall go back to that after this talk. One of the problems that's come up is using maths to help design ornamental flower arrangements. You know, you may laugh, but how many of you have given flowers to someone? You know, very important. And the number of applications in maths is just going padoink. But as I said in my last lecture, we have exciting times, but we do need to encourage people to go into maths or at least use maths in their work. So I think we are in a golden age, and I very much hope that will sustain. Okay, so where are we heading next? Well, good question. At the beginning of the 20th century, Hilbert, who one of the greatest mathematicians of all time, posed 23 problems, and at the Paris Convention of Mathematics, and suggested that those 23 problems would drive mathematics the next 100 years, and to a large extent, he got it right. Okay, so these are called Hilbert's problems, and lovely quote, "Who of us not be glad to lift the veil behind which the future lies hidden, to cast a glass at the advances of our science, and all the secret of its development during future centuries." And basically, he got it right, as I say. Most of his problems have now been solved, but not quite all. So, everyone thought, wow, beginning of the 21st century, where's maths heading next? And an outfit called the Clay Institute published a similar list of challenges, not 23 this time, only 7, which have been called the 7 Millennium Problems, which are designed, again, to stimulate the progress of maths in the next 100 years or maybe beyond. Poincare hypothesis, which was the first of these, has actually been done already, so 6 to go. But here are the 6 remaining problems which are supposed to drive us forward into the next 500 years. Okay, I'm not going to go through all of them. I've only got 5 minutes left, but it gives me, I'm just going to go very, very quick whiz through 3 of the problems. One of them, the first one is the Riemann hypothesis. This object here is called the Riemann zeta function. It's a sum of 1 over n to the z, and where z is the number there. Euler, remember him, found a link between this and the primes, So this sum is equal to a product of the primes. He used that to show that the sum of the reciprocals of the primes was infinite, which allowed him to deduce that the nth prime number Pn was approximately n times log n. So he got a lot out of that. And 100 years later, Riemann, there's Riemann, in 1859, again, one of the great mathematicians of all time, studied the Riemann, the zeta function in more detail, and said, well, you could tell far, far more about the primes if something is true. And what he said would be true was if what we call the zeros of the zeta function all have the property that the real part of them is a half. Okay. What do we know about this? Well, not a lot. Millions and millions of zeros have been computed. Every single one has real part a half. There's currently no evidence at all that none of the rest of them do, but no one knows. Books have been written on this. Plays have been done on this. Films have been done on this, but no one knows the answer. Okay, so that's that one. Here's a simpler question. If you can find the sum of the reciprocals of the cubes, you'd be doing well. Second one, this is, these things here are called the Navier-Stokes equations. They're an extension of Euler's equations for weather. These are basically the equations for the weather. These equations we solve every day to predict the weather. However, we have a certain amount of faith in solving them because we don't even know if they got a solution. Okay. Tricky. The problem is, do these have a solution? Well, everyone's trying to think very hard about this. It's very closely linked to the phenomenon of turbulence, which Da Vinci studied, which is where you get lots of structure on small scales. An interesting enough, Da Vinci died in 1519. Have you heard that date somewhere before? So there's a nice continuity. Huge amount of works going into trying to solve these things, but we still have no idea whether they got a solution, and just look at all the applications for that. So this is an area I work in myself, and I'd love to know the answer. And the final big question is called the P versus NP problem, which is the big question of computer science. Here's the problem. Let's suppose the size of something we want to solve is n, that's maybe the number of digits. If I multiply two numbers with n digits, it takes n squared operations to do that. If I want to factorize a matrix with an n by n matrix, that takes n cubed operations. This is what we call polynomial time, and that's generally regarded as easy. If I want to factorize a number with n digits, it takes 2 to the n over 2 operations, which is called exponential time. This is phenomenally hard, and hard means useful if you're trying to build computer security around it. If I want to solve a jigsaw, which has n pieces, if I take one piece at random and then I take another one and take all possible combinations, it takes n factorial time, which is basically hard to do it. But I can look at a jigsaw and say, yeah, that's right. So it's very quick to check, and that's what we call NP. And the big question is, if you can check something quickly, can you solve it quickly? That's called the P versus NP. If we could solve that P equals NP, we could solve everything. The whole world could be done, including economics, cryptography, and Sudoku. But after years of searching, we don't know and we have not a clue, and it remains a huge challenge. And I personally think of that as my equivalent as the cubic, as the big challenge for the next 500 years. And I would be amazed in 500 years whether we solved it. But hey, what do I know? So kind of conclude, we started with the cubic. Who at the time of Thomas Gresham's birth would have known where that would lead to? And yet it's led to the modern world. I've given you those clay problems. Who knows what the solution of those will lead to? But much more interestingly, there's lots of questions out there. We don't know even what the question is, and they're going to be the most interesting of all. And there's bound to be vast numbers of these. And hopefully, when someone in 500 years' time gives a talk, they'll be talking about those and marking the year 2019 as a division between then ancient maths and then modern maths. Thank you very much.